Post this to my YouTube channel. All right, so we kind of left off somewhere around here, and we said epoxides, what they can do is they allow you to install two functional groups on adjacent carbons. Of course, one of those functional groups is going to be an alcohol. But remember, we said that the nucleophile could be a cyanide to make a nitrile. It could be a mercaptide to make a sulfide. It could be a hydride. It could be an alkoxide to make an ether. So here's an example. And what they're saying at the bottom here is that if you see two functional groups like an alcohol and a nitrile next to each other, they're saying you should think of an alkene as a starting material, right? If we were to start with this alkene, so 1-methyl cyclopentene, and if we treated that with MCPBA, what's going to happen in the first step is that we would make the epoxide, which is going to look like this. It's not the best drawing in the world. But anyhow, and then in the second step, the cyanide, which is our nucleophile, is going to come in and attack from the least hindered face of the molecule, or the least hindered carbon, I should say. And we end up with the nitrile and the alcohol in the same compound. So again, the idea is that if you see two adjacent functional groups, you should think of an epoxide, and of course you would make that from an alkene. Now where it gets more interesting, I think, is if you have a Grignard reacting with an oxirane. Well, in that case, if you treat it with methyl magnesium bromide, meaning an alkyl halide, after step one, just write it all out here, right? After step one, if you treat this with magnesium and diethyl ether, which you can abbreviate ET2O like this, so this is diethyl ether, okay? That's going to give you the Grignard. So if we have a Grignard reagent like this, then in the next step, when we treat that with, maybe I could draw that a little neater, when we treat that with oxirane, right, that's going to do a nucleophilic attack, and we're going to open up the ring, which is going to give us R with 1, 2 carbons, and then the alkoxide, and then in the very last step, we protonate it. And so if you see 1, 2 carbons, and then an alcohol, and of course we just have an R group here, you would want to think about doing a Grignard kind of synthesis like this. So the epoxide consists of a carbon chain that will be added to the alkyl halide. And this is something that we do, we look at quite a bit. I think there's a few practice problems in the end of the chapter that deal with this kind of synthesis. Now, what if you wanted to have the hydroxyl on the first carbon, right? We just looked at the strategy where you end up with the hydroxyl on carbon number 2. What if you wanted to have it on carbon number 1? Like this, well, in that case, you would use a carbonyl compound, okay? In this compound here, this compound has a name. This is called acetaldehyde, okay? The name is neither here nor there, but I'm telling you because it will show up later on in this course. It's an aldehyde, acetaldehyde. And so what's going to happen here is in the first step, after you treat that with magnesium, you end up with your Grignard reagent, right? So there's my Grignard reagent. And then that's going to react with the carbonyl, right, by doing a nucleophilic attack, right? And so we're going to end up with, and if you can follow my arrow here, we're going to end up with this, where we have this alkoxide, and then in the last step, we do the proton transfer with water. And so again, if you have the hydroxyl on the first carbon after the R group, you'd want to think about using a carbonyl. So let's say we wanted to do this reaction here where we're taking bromobenzene. So this is called bromobenzene. You can see it's got 6 carbons. It's an aryl halide, and we want to convert it to this alcohol. And this alcohol has 6, 7, 8, 9 carbons. So we're adding a total of 3 carbons. Well, we could make this from an epoxide, couldn't we? If we were to take the bromobenzene and treat it with magnesium and diethyl ether, that's going to give us the Grignard reagent. And I'm going to draw it as a carbanion just to make the rationale easier in my brain. And then if you're wondering, now what's the electrophile going to look like, right? It's got to be a 3-carbon electrophile. Now this is not correct. This is something I do with my students. If you think about these arrows being drawn, or this arrow being drawn backwards, right, in a retrosynthesis, that would give you an epoxide that would look like this, right? 2-methyloxirane. So if we treated this compound with 2-methyloxyrane, right, this compound, it's going to attack at the least hindered carbon. We're going to pop that ring open, and we're going to end up with this. So if you number the carbons, 1, 2, 3, we're going to end up with 1, 2, 1, 2, 3. And on carbon number 2, we're going to have the alkoxide. I like that. So we'll number these as being 1, 2, and 3. And then in the very last step, we're just going to do a proton transfer. So we can draw the mechanism of it, which looks something like this. There you go. And that gives you the desired product. So this thing here, this is a Mr. Dion thing. That's not a correct arrow. That's not even a correct retrosynthesis arrow. But I've taught the class enough to know that it seems to help students to make the connection between the oxygen and carbon number 1. And then they just kind of figure out, well, here's my 3-membered ring here. And they're able to come up with the epoxide that way. If you find it useful, then use it, even though that curved arrow was totally incorrect, right? It's going in a backwards fashion. And so there's our whole synthesis laid out for us. You can see that I put water in the last step. Again, you could do water or you could do hydronium. I think the hydronium is more correct with a green yard. So maybe I'll just replace that like this. There we go. All right. So there's the whole synthesis laid out for you. Okay, and so what we're going to do next class is we're going to take a look at these syntheses here. So 13.22, we're going to look at these on Wednesday. And then I have some other syntheses here, and these ones are more challenging, but we're changing the carbon skeleton. You can see we're starting off with bromocyclohexane for all of these, but in this one you're adding 2 carbons, and this one you're adding a total of 4 carbons, and here you're also adding 4 carbons. So I want you to try these, and if I can make a recommendation, I know a little bit, after having taught the class many times, especially for these ones here. I'm not going to write it down on the screen, but try them without looking at the solutions manual. See if you can go through the textbook, like actually through the text, and figure it out without looking at the solutions manual. If you think you've got it figured out, then look at the solutions manual. But another thing you want to remember is that you might need to use some reactions from previous chapters. Okay, so we're going to have to maybe incorporate some oxidation chemistry and stuff like that. Some might be acid catalyzed ring openings, some might be nucleophilic, depending on the situation. I'm not going to give you the answers right now, but we're going to take a look at these next class. And also, if there's any questions that you have from the recommended, and when I say recommended, I mean you should do all of them, the suggested practice problems from the back of the book, if there's any of those problems that you want to do, you let me know, and I'd be more than happy to do any of those problems. And then on Wednesday, we're going to get into chapter 16, which I said isn't the longest chapter going or anything, and then we'll be able to finish it up on Friday. So I'm going to write here on the very last slide, I'll put here Wednesday. We're going to look at those two.